So a while ago, probably a couple months ago, I got a question in the comments asking how to use the implied volatility code to do several implied volatilities at once. In other words, how to vectorize that code. And at the time, I was kind of not thinking about it that clearly, and I was like, well, you're probably gonna have to do a loop. And then, of course, as soon as I posted that, I realized how simple it was to do that vectorized code. So I wrote it up in kind of a test format, and it didn't work. Well, it worked poorly. Let's put it that way. So what I was going to do is do a video on how to vectorize that implied volatility code and how to debug these sorts of problems. But that whole video essentially went off the rails. It needed too much explanation, and I wanted to do some other things like why do this vectorization in the first place? Why not just do a loop? And it was just becoming too unwieldy a video, too many concepts, and so I eventually scrapped it. But I want to get to it eventually, and so what I think I'm going to do is another how to debug one of these types of coding projects. So we're going to take a look at Newton's method and try to figure out why it fails just in some generic things, and then we're going to look at a non-vectorized implied volatility problem and see if we can apply the same logic to that and see where it can potentially go wrong. So yeah, let's get started. Okay, so in a notebook, I'm not going to build most of this live since we've already done a lot of it before. So I'll build it in chunks off of the recording. But if you remember, the procedure for applying Newton's rule to find roots is basically this. You choose an initial guess of the root, calculate the first derivative, and using that you basically construct the equation of the line, the tangent line that goes through that point. You look at where that line crosses the x-axis and you use that as a new guess for the root, and you update until you reach some desired tolerance. Now what we're going to do is choose a very simple equation here, just a cubic equation. Y is equal to x minus 1 quantity cubed plus 5, and I've calculated the derivative here. It's y prime. The derivative is equal to 3 x minus 1 quantity squared. And we're going to just look at this, calculate the roots of it using Newton's method, and we're going to look at places where this algorithm might fail. And then eventually we'll move on to the much more complicated Black-Scholes model and calculating the implied volatility. So of course the imports, and I've already written the functions here. So I have a function cubic that returns that cubic equation, a function here which returns the derivative, and I've written it this way because we're eventually going to write a Newton's method function that's going to take an argument, a function argument, a derivative argument, among other things. So I'm explicitly writing these as individual functions. And I've also written a function here that's going to calculate basically draw out a tangent line, calculate the xy points to draw out something that looks like a tangent line. So down here I just plotted out what this function looks like. Again, it's a cubic, it has an inflection point, and this particular one has only one real root, which is a negative value, which looks to be about negative 0.75. And I'm going to come up here and arbitrarily choose the value of 2 to be my first guess at the root. So I'm going to come up here and calculate the derivative at x equals to 2. So I'm going to calculate a y prime is equal to cubic derivative at 2. So let's calculate that. Let's just print it out just to have it available for us. So print y prime. So there we go. The value is 3. In fact, let's just change the way we code this and change this 2 to an x naught, and we'll come up here and say x naught is equal to 2. So we do that. Okay, and let's calculate the equivalent y value at 2. So let's go up here and we will say semicolon y naught is equal to cubic x naught. Okay, so now let's get some points to plot out the tangent line, and we'll call those the x and y values u and v respectively, and that'll be equal to tangent line. The slope is y prime, the derivative, and we want it at x equals to x naught and y naught. Okay, and let's just plot those now. plt.plot u comma v, and we'll make this a black line. Okay, and now let's just extend that out and make it a little bit longer. So what the argument is length. So let's do length is equal to, I don't know, it looks like it's going to cross the x-axis maybe 3 or 4 times longer than it is. So length is equal to 4. I need a comma here, don't I? Comma. Awesome. So just eyeballing it, the new value of the root looks to be close to 0. So I put in the equation for the intercept here and printed it out, and it actually turns out to be exactly 0. So that's cool. So let's plug 0 in for our original guess. Where was our original guess? Up here. So let's do that and see what happens. So if we come up here and we change this to 0, we get a new value of basically minus 1.3. So let's copy this. You can see this tangent line is shifted. So let's copy this. That'll be close enough. Come over here. We get another value of minus 0.8. So you can see we're getting closer and closer to this actual root. So let's just do one more iteration here, and let's copy this. Come over here. Delete, delete, delete. Paste. Oops. So where are we now? We're about minus 0.72. So let me just come up here and actually shorten this length a bit to 2. Just so everything fits nicely. So you can see what's happening here. We're getting closer and closer to what should be the actual root. And now, since we've already done this in the past, what I'm just going to do is copy and paste in a function that does this iteration process for us. Okay, so I've written a function called Newton's method, and this is basically the same thing that we have here for our original implied volatility script. It's just generalized to take any function. So the arguments are the function we're trying to find the root of, a function that returns its derivative, and the initial guess of the root, which I called r, and it defaults to 0 if you wanted to, but you could set it to whatever you want to. Maximum number of iterations, which just keeps this thing from running away. When we go on to the implied volatility in Black-Scholes, we're going to need to pass in additional arguments, so that's what this handles. And then I have a debug flag, which defaults to false, but it'll print out some information if it's set to true. So basically, this here just keeps track of the iterations and breaks if the loop runs away. We store our old value. We figure out the value of our function, its derivative. We update the guess of the root, and if that root is within some tolerance, this tolerance will eventually kill this while loop. So let's run this function on our cubic equation down here and see what we get. So let's see. Let's just say root and then the count. The function also returns the number of counts it takes, number of iterations. So root and count is equal to Newton's method. Oops, what's going on here? Newton's method. Our function is called cubic. We need to pass in the derivative, cubic derivative. And we need an initial guess, and I believe, if I remember correctly, we use 2. So let's just say r is equal to 2. And let's just print out r and how many counts it takes, how many iterations. So we get a minus 0.7-ish type of thing, which is what we expected here. We'll plot this point on the graph in a moment, and it took 6 iterations. But we are getting a warning here, which I did not really expect, a divide by 0 error. So we'll come back to this in a bit. But first of all, let's just plot this root and make sure it makes sense on this graph. So I'm going to come up here and just copy the code we used to plot this. So let's come down here, plot it, and now let's plot plt.plot r and cubic of r, and we'll make it a circle. Looks perfect. So I'm going to shut off the recording and add some headers in here because I want to keep all of this this previous stuff we've done so that for debugging purposes we can go back to it at a later time and perhaps investigate this divide by 0 error. So I'm going to shut off the recording and do that now. Okay, so I put a little bit of markup in here. So this section is going to be cubic equation, and this is our manual iteration where we were manually just going through this, and I took out the output just so I could work with a clean notebook. So this was our manual iteration. This was again, this was our functional solution to the problem with an initial guess of r equals 2, or root is equal to 2. This, remember, produced this little warning but gave a correct result. And what I want to do down here is just put a different result, a different initial guess in. So r is equal to 3, our initial guess. And what I'm going to do is copy this entire block, paste it in down here, and then change this to 3 and see what we get. Okay, we get the same root basically. It takes 6 iterations. We do not get a warning this time, and then of course it plots it, and we get the same root essentially as before. So, okay, let's put in a few different values. So, let's try r equals 1 and r equals 0. So I put in these markdown headers or markdown cells. And let's just do r equals 1 first. So we're just going to copy and paste our code block in, and we're going to change our initial guess to 1. Huh, interesting. Not a number. Weird. Okay, let's come down here, paste it in. R equals 0. Again, we get a warning, but it does seem to come up with the correct root. So what's going on here? Our value of 3 works perfectly. Our value of 2 works, but we get potential warning messages, which should raise a red flag, because you probably don't want that in production code. 0 does not work at all. It gives you, no, 0 works. It gives you that warning again, and then 1 gives you a not a number, so it fails completely. So what's going on here? Let's start first of all with, we're going to look at r equals 1. And come back and start and go through our, where's our code, where's our function, here it is. So how might this thing go wrong? It's obviously not getting caught in an infinite loop because we're only doing at most 6 iterations, and where it fails the worst, where it gives you a not a number, it is only 2 iterations. Well, you could get a not a number if your function returns that or its derivative, but our functions are very well behaved, and that's the reason I chose these. It's just a cubic. Its derivative is just a quadratic, so it's probably not that. So what else could it be? Well, if we were to get a 0 derivative down here, this might be an issue, right? Because we divide, if this is a number and this is 0, you get a divide by 0 error, so that might be the case. Another possibility is we're doing the same thing here. If our root is initially 0, this epsilon that we use for a tolerance might come back as infinite or not a number or something that's problematic. So as you can see here, I have a debug statement here. So if this is equal to true, it's going to print out the function value and its derivative. In fact, let's also do that down here. Let's come down here and go if debug is equal to true, print, let's do print tol is equal to epsilon. And in fact, up here, let's put f is equal to that, just so that we have some clarity as to what numbers it's printing out. And over here, put f prime is equal to that. So, does this run okay? No errors. So when we let's actually run some of let's go to the 0 one here and run it with that debug flag set to true. So where is my 0? There's 3, 1. Actually, let's do 1 first. Let's do this one first and set the debug equal to true. So you can see what happens here. We get a derivative equal to 0, which causes everything to basically be infinities. So that's why that's failing. So obviously the 0 is an issue. Derivatives close to 0 can be an issue. 2. I don't know what's going to happen here, so we're going to find out together. Let's change 1 to 0 point, and let's just do a whole bunch of 9s. Run. Okay, it seems to actually run. Does it give a correct result? Come on. It eventually gets there, but it takes a whole bunch of iterations. It takes 118 iterations. And what's the derivative initially? So 10 to the minus 20. I'm actually surprised that this code actually converges to an answer, because you're going to see when we do the Black-Scholes model, we're going to have points where it just does not, you get derivatives like 10 to the minus 16, which is close enough to 0 that it's not going to converge. And I think the reason it does here is because this function only is kind of that shallow slope for a very short time. And in the Black-Scholes model, you can potentially have areas where it's essentially 0 slope over an extended range of x values, or in that case, sigma values. So interesting. I did not expect that to happen. I thought it would fail, but it eventually gets to the right answer. So let's just change this back to 1. Okay. Now that I think about it, the actual issue for the Black-Scholes model when that happens may not be the slope per se being close to 0, but the fact there's a discontinuity. And if you have a slightly positive but not 0 slope, it will never quite find the intercept on the negative side, and hence will never converge to an answer, proper answer. You'll see it when we plot it out. It should be evident. So before moving on, I just want to plot out the tangent line at our initial guess for this one, for r equals 1. So let's come down here, and we will do what? Let's do u comma v, and that's equal to tangent line. The slope is cubic derivative at 1, and the point will be at x is equal to 1 and y is equal to cubic of 1. Let's see if that runs. It seems to run okay. Let's come down here and just plot that. So come down here and we will go plt.plot u comma v, and we will make it a black line. So actually, let's make it a little longer in the x direction. So length is equal to 4. Let's make it 3. So there's our tangent line, and you could see the interpretation of that divide by 0 error. This is going to fail because this is never going to cross the x or cross the where y equals 0. So there is no intercept. So let's come down here and look at r equals 0 now. Let's run that. Okay, it gives a warning. Let's come back here and just do a debug equals true. Debug is equal to true. Run that. So as you can see here, we're getting a tolerance of infinity, and that makes sense because our initial guess of the root is 0. So if we go back to our code base here, where's my function? It's figuring out the new root, and then it's trying to figure out the percent change. Where's my percent change here? Here it is. The percent change is just equal to the absolute change kind of divided by the original value, but the original value is 0, so we're getting a divide by 0 error. In this case, it's not a big deal because NumPy is interpreting that as infinity, so it's just basically saying we haven't reached this tolerance, and this tolerance is not converged, and we go on to eventually get to the proper answer, as you can see from this graph. So I'm going to shut off the recording and add some notes to these header fields, just so more for my benefit than for yours, just so I know why these failed, and yeah, just basically to document it. So I've added some notes here for the case of 0, just as we said here, that initial guess of 0 causes the tolerance check that to return an infinity, which doesn't crash things, but it does create that warning message. For this one here, it's a bit more complicated. We get a 0 derivative, which causes the update basically to fail. So we get a x-intercept of infinity. So that's a problem. It also causes the tolerance to return an infinity. And so eventually we get in the next iteration an infinity over infinity, which is here, and that causes the tolerance to be not a number. So let's just quickly come back here. 3 works perfectly. Let's go back to number where we picked 2, and let's I have a warning given, reason unknown. Let's just see if we can quickly diagnose that by setting debug equal to true here. Debug is equal to true. Oh, and I did make one change to the code, just because it was kind of ugly. Instead of having to print out all these function information and derivative information on its own line and then the tolerance stuff on its own line, I just combined it all, and I also printed out the iteration here. So let's go back to number 2. Let's just run that. So we're getting a tolerance of infinity on the second one, which means we're probably getting one of these root values to be 0 when it updates. So let's just check to make sure that's true. We can steal some of this code we use for our manual iteration. Where is it? This. Copy. Let's come down here and paste it in. And then steal this line here. Come on. Where are we? Paste that in. Set this equal to 2. And we see estimated root is 0. So that's why we're getting that that particular error or particular warning message, because one of our roots comes back to 0, and then we check the tolerance dividing through by 0, and that's the cause of that. So I'm just going to change this. So now that we know the cause of that, I will just update this part, and then we'll move on to actual Black-Scholes model. I've noticed we're kind of actually running a bit long here, so what I might do is split this into 2 parts and do the Black-Scholes in the next section. And I just want to say a few words about this function here and a couple other simple cases. Where's my original function? Here it is. I chose this. Let's use this one here. I chose this for a reason, because it's a well-behaved function, and it has only one real root, and yet it could still cause problems depending on how you define that tolerance cutoff thing, or if you have a 0 derivative here. Other functions that are just as benign can also cause problems. So let's come down here and we'll define a quadratic equation. np.power x comma 2, so there's our quadratic term, and we're just going to have 9 here. So this equation obviously has 2 roots, plus or minus 3. Let's just plot it out here. Let's go x is equal to np.lin space, let's go from -5 to 5, 100 points, plt.plot x comma quadratic. Come on here, quadratic of x. So quadratic of x, and we'll go with a blue line. So there's our plot here. Now this obviously has 2 roots, so which root we get depends on where we choose our initial values. So let's define a derivative equation here, just so that we are consistent with our formats here. So define quadratic derivative x, and that's going to return 2 times x. Now this should also throw an error if we pick 0 as our starting point, because here the derivative is 0. So let's actually just see that that's the case, and we will come down here. Let's do it right here. We will print Newton's method Newton's method, our quadratic derivative. I know that it defaults to r equals 0, but I'm just going to explicitly say it. So let's see what happens here. Oh, that's right. This needs an args argument here. Args is equal to empty list. Let's come down here. Args is equal to an empty list. not a number. That's not surprising because, well, we just went through it. The derivative is 0 and you're getting a divide by 0 error. So let's come over here and set this to 1. We get a positive 3, so that's over here. Let's set it to, I don't know, let's set it to 5. Again, positive 3. If we set it to minus 5, it's probably going to come and find this root at minus 3. Let's see if it does. Indeed it does. So in this case, it's obviously sensitive because there's multiple roots to where you start the search process. And in this case, we know there are 2 roots, so we could be careful, but in general, you're not going to know how many roots your function has, so you have to be careful on how you set things up. Yeah. Now this function here is very well behaved. You could have something different. Let's come down here and just look at the tangent of x. So I'll come down here, we will define, let's just call it tangent x. And we will return, we're going to need that args variable again, or args argument, args, return np.tan x. We're going to need a derivative, so def tangent derivative x args is equal to an empty list. Return, it's np.secant of x, and I believe it's that squared. So let's go np.power 2. So let's go x is equal to np.ln space. Let's go from minus pi to pi, minus np.pi to np.pi. We'll do 100 spaces or 100 entries. Okay, sorry folks, the audio just went a bit wonky there, so I have to re-record a bit here. So what I was saying is there are discontinuities here, there are singularities every, with a periodicity of pi here, every, minus pi over 2, and then so on. So that can cause some potential issues. But what I had done here is I put an initial value of 1, and it does converge. It gives you a value of 0, a root of 0, which is correct. 6 iterations, although there are some issues here. So if we change this debug to true, we get not a number, and that's probably in the tolerance, and that's probably because that divide by 0 since the root is 0. And one potential way around that divide by 0 in the tolerance error is just to change that to some sort of absolute tolerance, or not divide through by the old root, so that we're getting basically just a distance. So let me plot that point here. Let me come down here and go plt.plot. Let's plot R0, and we will plot tangent of R0, and we will just do a circle like we've been doing. What's going on here? Oops, there should be a parenthesis here, and then not here. So there we go. And plot rather than plit, or plot, yeah. So that's cool. Obviously, it's going to have the same issues with not being able to find the right, find the particular root you're interested in if we're in the a different place. So if we set this R equal to, say, I don't know, 7, it finds a root out here. Let's extend this out to 7 and see if it's actually a real root. Looks that way. So let's turn it back to 2 pi, or pi, np.pi. Let's be a little silly and intentionally set this here to np.pi divided by 2. It gives a root of 1.5, which looks like it's going to be basically infinity. So obviously this is wrong. So let's print out the function value there. So let's print tangent R0. Oh, come on. Sounds like my phone is going to blow up next to me here. These people are just insane with their chats. It's really annoying. So there we go, 10 to the 16. So that's obviously a bad value. Bad value. It's just blowing up because of that infinity. Okay, I'm going to call it quits here and move on to part two in a little while, because this phone is really pissing me off and is distracting me, and I can think even less than normal. So until part two, we will see you.